Okay, so this is going all the way back to the beginning to just kind of set up this next thing. So we looked at water evaporating or condensing at different temperatures. Remember this? We talked about entropies and how entropy changes and how the entropy of the system changes by some amount, but as long as the entropy of the surroundings changes by more in a positive direction, then that would be spontaneous. Bless you. And actually, wait, no, maybe the side I'm thinking of also is later. Because we got to give free energy. Yeah, and then we calculated, I think we calculated this for water evaporating at some point, maybe? No? Oh, these are the relative entropies. I thought that this was somewhere, or maybe it's just in the textbook. Hmm. Hmm. Nope, I guess it's just in the textbook, right? So, we looked at water. We looked at how water, right? We said water freezes spontaneously below 25 degrees C. It should melt spontaneously above 25 degrees C. Or sorry, above 0 degrees C. And then water boils, right? Spontaneously becomes a gas above 100 degrees C. It'll condense spontaneously below 100 degrees C. But water at room temperature also evaporates. And that's a liquid turning into a gas well below 100 degrees C. I kind of wanted to avoid the slide because the slide says why, but maybe you got to think about really why. So all of our standard conditions assumes that our gases, if we have a gas, is at 1 atmosphere of pressure. But, and this is fresh on my mind because I'm teaching it in Chem 20, we just talked about partial pressures of gases, right? If like regular pressure at sea level is 1 atmosphere, if the partial pressure of water was 1 atmosphere at sea level, then the air would all be water. It would be all water vapor. There would be no oxygen or nitrogen. So clearly we're practically never at standard conditions, right? So the reason that water just evaporates is because it's not standard conditions. And so we have to sort of take into account this fact that like a lot of our reactions not going to be happening at standard conditions, going to be a lot less than the partial pressure of 1 atmosphere under ordinary conditions. And so our process then, the delta G is not this positive 8.59. It is under standard conditions, but what is it then under like regular conditions? And how do we say what it is under any conditions? And to do that, we can add in this new factor RT ln Q. So Q is the quotient, just like we talked about with equilibrium, where Q was when we're not at K, right? K is at equilibrium, Q is at anything that's not equilibrium. For the really simple equation of H2O liquid to H2O gas, how do I calculate Q? Yeah. And like we didn't do a ton of these, right? So this is the water is a liquid, so products over reactant still. The bottom is just 1 because we're leaving it out, but we can't divide by nothing. And then for the water as a gas, it's going to be the partial pressure of the water as a gas. So the equation ends up being really, really simple. And then what if my partial pressure of water is 1 atmosphere? What is Q? It's 1. And the natural log of 1, 0. So when we're at standard conditions, Q is equal to 1. Natural log of 1, it disappears. And then we get times 0 times RT is 0. So that's why standard conditions is this delta G. But now you got this other factor that says, like, if we're not at standard conditions, if we're at anything else, and we're using the energy gas law constant, it is fundamentally the same thing as 0.0821 atmospheres liters per mole Kelvin with different units. So if you enjoy math puzzles, figure out how to convert this into 0.0.81 or 821 atmospheres liters per mole Kelvin. So with this, though, we can say, like, for gases or for other reactions that aren't at our standard conditions, where the concentrations are 1 molar or the partial pressures are 1 atmosphere, we can say if it's going to be spontaneous or not, because that modifies our delta G at standard conditions and lets us calculate what my delta G is at a non-standard condition. So in a sense, by plugging in Q here, we're calculating the analogous Q of free energy. So what my free energy is at some other thing other than the standard. And we can see, like, if we were to plug in a whole bunch of different values for Q, right? If we make the partial pressure of water 0, which is where Q would be equal to 0, my free energy would be really high, and this would be spontaneous because I'd be, again, moving downhill. So, like, any change on this graph, going from, like, here down to here, that would give me a change in, like, the delta means change in. So it'd be negative. I'd be going down towards that place where it is at equilibrium, where delta G is equal to 0. So if we think of, again, the chemical potential, free energy, is like mechanical potential energy. This is going down to some minimum. The minimum free energy is at equilibrium, which is why everything goes to equilibrium. Because when it's at that state, it's balanced. And it's at the lowest energy that it can be at under those conditions. Like, if we change temperature, then this all changes. At least some. So at equilibrium, right, we can plug in 1, but if we're at anything other than equilibrium, like 0.0, or sorry, no, this would be equilibrium at 25 degrees C. And then we can calculate that delta G of the reaction is equal to, and we're given standard conditions as a positive 8.59 plus R, which is 8.314, and temperature, which is 298 Kelvin, has to be in Kelvin. And then the natural log of 0.0313. I did this math earlier, but this comes out to really close. I wish they had used, oh, no, because you got to add, yeah. In this class, we're using, so this would be 25.00 plus 273.15. So it gives me 298.15. So this does work out then. Now this, when you calculate it, will give you an answer in joules. The reason it gives you an answer in joules is because R is 8.314 joules per mole Kelvin. So this ends up being like 8,586 joules per mole, and it ends up being a negative. That's a positive, so delta G of the reaction equals 0. We can convert this just by adding the decimal. So if we can actually calculate the equilibrium of a system, we can calculate the delta G. We can calculate the free energy at standard conditions. So for any of those reactions that we did like super early in the class where we did those equilibrium things, you like measure the concentrations, or for like acid-base reactions where you figure out all of the things at equilibrium, you could use that then to calculate delta G for that reaction. Now it would be delta G of the non-standard conditions, but then we would know what delta G is at standard conditions, because at standard conditions, the two added together should equal 0. And this is maybe something I want to do in Friday Night Lab, because like, why don't we have an experiment that does that? That sounds neat. We're gonna see some other cool stuff that you can do, right? This delta G is super powerful because it tells us if reactions are spontaneous or not. And we're gonna look at one example that the book gives of how this might be used, possibly. So we can calculate for other non-standard conditions. So like if the partial pressure of water is 5 times 10 to the negative 3 atmospheres, this is the next problem. No, it's not. Calculate delta G of the reaction. So delta G of the reaction. So without the little 0, that little naught, the O, kind of looks like a degree. That's non-standard conditions. It's going to be delta G of the reaction at standard conditions plus RT natural log of Q. And we have this was 8.59 plus 8.314. And I guess we're assuming the same temperature. Stop. There you go. Natural log of. Oh, and I guess I should pause here, right? The partial pressure for this problem, Q is equal to the pressure of water in the vapor phase, because my other part of this reaction is water as a liquid, which we leave out of the equation, right? So I can plug this straight in because I have one product, and that one product is the only thing that is included in the calculation of Q, the law of mass action. And then this is going to be 8.314 times 298.15 times the natural log 5e negative 3. So this is plus 13,133.57 joules per mole, which we got to convert to kilojoules. It's negative. So delta G is negative 4.54 kilojoules per mole. So still spontaneous. If we want to calculate this for like anything else, we just need to know what all the concentrations are, or the partial pressures, and the delta G at standard conditions. So here we're doing 298 Kelvin. We've got this reaction. I need to calculate Q. How do I calculate Q? Almost? You say over sulfur? Yeah, products over reactants. Except sulfur here is a solid. Yeah. Honestly, when I was writing it out the first time, didn't see it either. And then I looked at the partial pressures given. I was like, that's weird. Sulfur's not in there. And then I looked back at the reaction, solid. So just got to keep an eye out for those. Obviously, if you're given pressures, though, like you're not going to be given the pressure for a solid. It's not going to be included. But it's the partial pressures of the products over the reactants. This will be the partial pressure of H2S, and these are raised to their coefficients. This is 0.0100 squared over 2.00 squared times 1.50. That's 1.67 e to the negative 5. So not K. Keep wanting to write K. Later it'll be K. Right now it's Q. So we want to know, is it more or less spontaneous under these conditions than under standard conditions? So under standard conditions, it's negative 102 kilojoules plus 8.314 times 298 times the natural log of this is plus a negative 272. That makes sense. 53, but in kilojoules, 27. So this is negative 139-ish. Honestly, when we get to this point, we can answer the question. Is it going to be more or less spontaneous? More spontaneous. So I've got a negative number. I'm adding another negative number. It's more negative. $29-ish. So still more negative. Okay. Oh, I left that on there. So delta G of the reaction determines the spontaneity of the reaction. K determines how far a reaction goes, which like before we were kind of using K, we would say like if we add something to that reaction, either into the products or the reactants, using Le Chatelier's principle, it will shift the reaction. And that's because we've changed the balance of the reactants and products. And in essence, we've changed where the low point is in energy. So the reason that K determines how far something goes towards products is because it's related to delta G. Because at K, that's the low point in the energy. There's some curve. That's energy. The low point's here. That's K. And so for things with a large K, all right, and then we can derive the relationship. That's what this was. So you derive the relationship between the standard free energy, delta G naught, and and equilibrium constant K, because at equilibrium, since that energy is at its minimum, the Gibbs free energy there is 0. And so I set, I really say that on here somewhere, right? At equilibrium, delta G of the reaction equals 0, which is super important. And that also means that.
Is the lab open? I got the oil.
No, the lab's not open.
Where can I put this?
Leave it here. I'll put it in there. Oh wait, no, Andy's got a doorbell.
Okay.
Ring the doorbell and tell Andy that you brought cooking oil.
Sorry.
Is she not here in the morning even? I thought she was here in the morning. Maybe she's not here in the morning. I don't know. Right, okay, so we can set like the relationship between the standard free energy and K. So negative RT ln K is equal to the standard Gibbs free energy.
And you can substitute in K instead of Q because K equals Q at equilibrium.
Yes. Q is the same as K at equilibrium. So we can just swap that out because we're saying this is at equilibrium, which is the reason that we can make delta G of the reaction 0. And so now if we have K, that tells us something about where the Gibbs free energy lies in terms of where that low point is in relationship to my reactants and product concentrations. So something that is a very large K favors the products, which means that my lowest energy point will be when I have mostly products. And when I have a very small K, that means that the lowest energy point is when I have mostly reactants. And so then the reaction will favor reactants. But just like water flowing downhill, it's always finding the lowest point. And this is maybe where we're going to have, well, this is where we start having like more uses of essentially the same reactions with some special considerations. So right now we want to calculate delta G, standard delta G, standard free enthalpy or entropy at 298 K, and we're given K. So it doesn't tell us that it's at equilibrium, but that's kind of the only information that we have. So this is going to be delta G standard of the reaction is equal to negative RT ln K. And honestly, it's an easy enough thing to derive. Right, because really we're coming from this RT ln Q. But when we're at equilibrium, Q is K. So I swap in K. At equilibrium, I'm at the lowest energy point outside of standard conditions, which means that my delta G of the reaction is 0. This gets substituted in with K, and then you just solve for delta G at standard conditions. Standard free energy. So, and this is 8.314 because that's a constant. 298, that was given. Natural log of 81.9. I guess we could make a prediction about this too. Is it going to be positive or negative delta G? If it favors the products, it'll be negative. The other way to think about this is, right? It starts out negative. So the only way that this equation changes signs is if the natural log, I'm taking the natural log of something less than 1. Otherwise, this will always return a positive number. And then I multiply that by the negative, and it becomes negative. So this ends up being negative 10.9 kilojoules per mole. So spontaneous, 10.9 kilojoules. And again, like if you can find the equilibrium concentrations, or in this case, partial pressures of a reaction, you can calculate standard delta G. And I believe this is part of the reason that standard conditions is at 25 degrees Celsius and not at 0 or 100. Because room temperature is like, well, it can be anywhere from like 19 to 22 degrees Celsius. And so to get to 25, you just have to warm things up a little bit. And it's a lot easier to warm things up a little bit above room temperature than it is to cool them down. So we could take this reaction and do the reaction, get it to equilibrium, let it cool to room temperature, warm it up a little bit, measure concentrations, calculate delta G at 25 degrees Celsius. Now we can also draw some other relationships, and the book doesn't really use these. But if we take this fact that we have another way of defining delta G, like standard free energy, I can take this and I can plug it into here. Or I could go the other way. Actually, it's easier to go the other way. Both ways will get you the same thing. But if we plug my negative RT ln K in for standard free energy, then I get negative RT ln K. Actually, I don't know that it's easier. It just kind of works out a little bit better. Minus T delta S. I don't think the derivation of this is super important. So I'm going to go through it quickly. So I'm getting this over to the same side. I want to get K, natural log of K by itself. So I need to get rid of that T. If I move this over to having T, right, I've got something with T plus something with T. And then I can do this. Actually, I can do both of those. No, I can't do both of those. Negative R ln K plus delta S equals delta H reaction times 1 over T. And then negative R ln K equals negative, no, delta H, the reaction, times 1 over T minus delta S, and then divide by negative R. Yeah. It's like, woo, cool, neat algebra tricks. No, the point is, this gives us y equals mx plus b. And you might think like, woo, basic formula. The thing that's cool about this is that it says that the equilibrium, and we know equilibrium depends on temperature, right? If we change temperature, then it has an effect on equilibrium, especially if a reaction is exothermic or endothermic. And then we can even make predictions. But it means that if we calculate K for a reaction, change the temperature. Well, so measure concentrations, calculate K. Change the temperature. Measure the new concentrations, calculate K. Change the temperature. Measure new concentrations, calculate K. Now we've got a whole bunch of points. And if I plot that, then I'll get a plot of natural log of K as my Y, temperature is the x, and you get some straight line. And everybody loves straight lines. But also, this means that since this is the form of y equals mx plus b, my intercept is delta s. And the slope is delta H of the reaction, standard enthalpy of the reaction, divided by R. I guess this should be negative, huh? Well, no, it can be positive. If my delta H is negative, then I'll get a positive slope. So these values that we used for calculating Gibbs free energy, which we could potentially calculate just from K at a single temperature, or we could calculate across a bunch of temperatures, get delta S, get delta H, and then calculate free energy. Gives us sort of multiple ways to find the same value, which can validate our results, because we're basing it on sort of a bunch of relationships instead of just a single value. There's also a 2-point version of this where if you wanted to calculate it then at a new temperature, or if you had two temperatures, there's the 2-point form. The book doesn't have any examples of using this. So if I put it on the test, I'll give you some examples, or I'll find them on Alex. I did kind of want to give, I've got kind of a perfect amount of time. I did kind of want to give this context, why would we even care about doing this? The book uses one example where they talk about how hydrogen can be used in fuel cells to generate electricity for an electric car. Why would you want to do that? Well, the the energy density of a hydrogen fuel cell is insane. So it's 33.6 kilowatt hours per kilogram of fuel cell mass, which without any context, okay, whatever. But gasoline's 12 kilowatt hours per kilogram. And a battery in a Tesla is only 0.25. So what does that math work out to? Would it be 4 times whatever that ratio is? So 33.6 divided by 0.25, that's 134 times more energy stored. Hypothetically then, a hydrogen fuel system with the same mass as the Tesla battery could travel 134 times farther. And this is why gasoline is still better if you're going to do a cross-country road trip. It's just got higher energy density. I think the numbers that I saw for diesel were about the same, but I think it burns more efficiently. Now, the problem with hydrogen, though, is that it's really hard to store because it's really tiny. I think actually this is the reason that the Challenger rocket exploded, sort of tangentially. The O-rings in the Challenger rocket got too cold, and then that material became brittle. Why did they need O-rings? Because if you want to store a significant amount of hydrogen, you can't store it as a gas at room temperature. You have to compress it and cool it and get it down to a liquid form. That's the only time it's efficient. And so to do that, you need to both keep it insulated and have really good seals so that it doesn't get out. And so on the Challenger rocket, it got out catastrophically because the seals got too cold and the hydrogen escaped. If you get a car that has a hydrogen fuel cell system in it, you have to go to special fill stations where they fill your tank, you have a pressurized tank in your car of hydrogen, liquid hydrogen, I believe. And then the other problem with that is that it's hard to make. It's hydrogen's everywhere. In the universe, it's the most abundant element. I think online I saw it's 75% of the mass of the universe is hydrogen. On Earth, I think oxygen or iron end up being higher than hydrogen, but we have a lot of hydrogen stored in water. So what if we could use water, turn that into hydrogen gas, and then use that? The problem there is that it's not a spontaneous reaction. Actually, it's a good thing that it's not a spontaneous reaction because otherwise all of the water would just turn into hydrogen and oxygen. and there wouldn't be any water. So it's kind of good for us, but if we want to use the hydrogen gas, at least under standard conditions, delta G is positive 228 kilojoules, which is a lot. And so then the book proposes like, well, what if we could pair this with another reaction? So we do this other reaction where we take carbon monoxide, react that with oxygen, and turn it into carbon dioxide. And that has a delta G of negative 275.2 kilojoules, which is more negative than 228 is positive. So finding these delta G values, finding delta H, finding delta S, right? It's useful because it can help us to like propose different reactions. There's a lot of problems when you try to do this in practice, though. For one, this isn't under standard conditions. Two, it assumes that all of the free energy released by this reaction goes directly to the reaction that I want it to, and doesn't instead escape into the surroundings. The other problem is, like, well, yeah, because the main problem is like this reaction might happen and then it just releases all that energy as heat and it does nothing for my water turning it into hydrogen. I think this might be a known reaction. And then on top of all of those things, like if these don't interact, even if they could, they might react in different ways. So it can kind of provide us with a starting point for finding reactions and for proposing things. And like mechanistically here, there is a path forward because if I write these out, so H2 plus 1/2 O2, then the 1/2 O2's cancel, and it's carbon monoxide plus water. So at least those combine nicely in a way that kind of makes sense. But it won't necessarily happen that way. Plus 220.6. So in theory, this would be negative 28.6 kilojoules, which is spontaneous. I think there's one more thing that I didn't hit on. What might be another problem that free energy doesn't tell us about? Let's So start high, I end low. What do I know about what happens in the middle? Or does delta G tell me about anything that happens in the middle? Nope. So this reaction might happen, but what if it's really slow? We can't know from just this. Even K won't tell us if it's fast or slow. We'd have to do kinetics experiments to figure out if it's fast or slow, and even if it happens at all. So this is one of the things that we talked about early on, right? That delta G tells me between the beginning and the end, how does my energy change? If that goes downhill, then it's going to be spontaneous. If it goes uphill, then it's non-spontaneous. But it doesn't tell me how fast it goes from reactants to products. Okay, I guess we'll do redox next week.